Hey guys, this is Mrs. Harbin, and we are looking at Chapter 5, Section 8, Solutions to Quadratic Equations. Our biblical integration for this unit continues to be biblical imagery of parts belonging to a whole helps us to see that some numerical groupings can be broken into specific separate parts. So we've been looking at breaking apart quadratic equations to find solutions to those equations. That's involved some factoring, looking at factors of a product and other things. To carry this a little bit further, we know that parts belong to a whole, that we see that metaphor all throughout the Bible, that we are a part of God's whole creation, and it is part of our responsibility to help care for his whole creation. That's that biblical mandate. Our lesson objective for today is that you, the student, will identify the best method for solving quadratic equations and evaluate the discriminant to classify the nature and number of solutions to a quadratic equation. So we've been learning all these different methods for solving quadratic equations. Today we're going to identify which one is best to use for different problems. You're going to learn what a discriminant is, first of all, and then you'll be able to evaluate the discriminant so that you can classify what type of quadratic equation we're talking about and the number of solutions that that quadratic equation should have. This is really helpful. If you use a discriminant and you say, okay, using the discriminant, I can see that I should have one answer. And you go through and you solve the quadratic equation and you end up with two different answers, then you've done something incorrectly. And so using the discriminant can be kind of like a safety net to make sure that you have actually solved the quadratic equation correctly. Now, when we talk about solving quadratic equations, even though this isn't really taught explicitly in the book, if you look through the book, you won't find it. Remember that we're moving into graphing, and quadratic equations are equations that have a squared term. So they're second-degree polynomials. Typically, it's using an x as the variable. So quadratic equations have a squared term. And when we graph those make this lovely shape, which we call parabola, sometimes opening up, sometimes opening down, but they make parabolas. Parabolas cross the x-axis at two different points. If this is our Cartesian plane here, parabola might cross the x-axis here and here, or maybe here and here, or maybe they only touch the x-axis at one point, or maybe there's some imaginary numbers involved. But when we're solving quadratic equations, what we're really solving for are the places where it crosses the x-axis or touches the x-axis. We also call those the zeros of the equation. When we move into graphing these, and I ask you to find the zeros of an equation, hopefully you're not confused, because I've been mentioning this every single time we've done a lesson on quadratic equations. When you're solving for x, what you're really finding is where it crosses the x-axis or where it touches the x-axis. This will be super important when we move into graphing quadratic equations, when we look at quadratic functions and start to graph. So as we've looked at solving quadratic equations, we've seen four different techniques. The first technique that we saw was factoring. And factoring is what we should use when the polynomial factors easily, or when c equals 0. This is really the first thing that we should do when we're trying to solve a quadratic equation. See if we can factor it easily. Because you guys have been on break and maybe you don't remember what factoring is, what factoring is, that's the thing that we did where we used the x to help us factor. So we're going to use factoring, if we can, as our first attempt when the polynomial factors easily, or when that final term c equals 0. Just as another quick refresher here, our general form for a quadratic equation is ax squared plus bx plus c equals 0. C is our constant. It's the term that's just the number. So when that c equals 0, we can use factoring just right off the bat. Factoring should always be the first thing that we check. So take a look at this. X squared plus x minus 42. Now our c is not 0. C is actually negative 42. But if we try to see if it's easily factorable, we're looking for two numbers that when multiplied equal negative 42, but when added equal 1, that's in front of the x, a positive 1. And we know that a 7 and a negative 6, when multiplied, equal negative 42, but when added equal positive 1. So this polynomial, this quadratic, is going to be easily factored, and we can solve for x from there. Writing x plus 7 and x minus 6, we would then set each of those equal to 0. And we find that x equals negative 7 and x equals 6. So if we were to graph this, it would cross the x-axis at negative 7 and 6. The zeros of the equation are negative 7 and 6. A second method that we looked at just a class or so ago was taking roots. Because of perfect square trinomials, taking roots is another method that can help us solve quadratic equations. We would use this when b equals 0, or the polynomial is a perfect square. So this is referring to a difference of squares. I misspoke, not the perfect square trinomial, but a difference of squares. When we look at this, we have x minus 2 squared. There is no b term. We have an x squared term, but we don't have just a regular x term. And so when we've got x minus 2 squared equals negative 8, what we can do is take the square root of both sides. We get x minus 2, and then the square root of negative 8 is 2I times the square root of 2. In case you're not sure how we got there, here's a quick review. Negative 8 is just negative 1 times 8. Or if we do the prime factorization, it is negative 1 times 2 times 2 times 2, which we can rewrite as the square root of negative 1 times the square root of 4 times the square root of 2. 4 because we had a group of 2 here, perfect square. Square root of 1 is I, the square root of 4 is 2, and the square root of 2 we're going to leave alone. And so we are left with 2I square root of 2. Those are the steps to get from here to here. So that is solving by taking roots. We would write that as x equals 2I square root of 2 plus 2. A third technique that we looked at is the quadratic formula. And the quadratic formula is a formula where we really just plug and chug. And we're going to use this when the previous methods are difficult to use. When it doesn't factor easily, when we can't take roots, the quadratic formula is what we're going to use. So take a look at 2x squared plus x plus 3. If we were to try and factor this, we would want two things that when multiplied equals 2 times 3, which is 6, and when added equal 1. Well, there aren't any numbers that when multiplied equal positive 6, and when, I should say positive 6, not 16, and when added equal positive 1. So it's not easily factorable. And we have a b term, so we can't take roots, so we've got to go into the quadratic formula. Completing this square is a fourth and final method, and you're really only going to use this when you're directed to do so. It is important to know how to complete the square. It does give us information that we need. It's where we get the quadratic formula from, but for right now, you're only going to use completing the square if you are directed to do so. And so in this equation, x squared minus 6x plus 4, again, it's not easily factorable. You can't take roots, and so you might be told instead to complete the square. I haven't shown you how to do those two by completing the square. If you would like to see those step by step, the quadratic formula and completing the square, you can look at those on page 218 of your book if you would like me to go over this with you and show you how to do those two particular problems. Let's take a look at this example. 3x squared equals 54. Which technique do you think we should use? Hopefully you notice that there is no b term, there's no just plain x term. So since b equals 0, we can solve by taking roots. The first thing I need to do is get the x squared term by itself, and I do that by dividing both sides by 3. Now that x squared is by itself, I can take the square root of both sides. The square root of x squared is x, and the square root of 18 is 3, square root of 2. We're going to simplify that square root of 18 by using the prime factorization, or looking for perfect squares. 18 is just 9 times 2. I know the square root of 9 is 3, and the square root of 2 I can't do easily, so the square root of 2 just stays as is. X equals plus or minus 3 square root of 2. Let's try this one. 4x squared minus 12x equals 0. Which technique should we use? Hopefully you notice that there's no constant term, so our c is 0. When c is 0, we can use factoring. We're going to start by factoring out what they have in common, and both of these have a 4 and an x as factors. when we factor out what they have in common, our first term still has an x remaining, and our second term has a -3. To make sure that we factored correctly, we can distribute that back, multiply it back out to make sure that it does equal 4x squared minus 12x, and it does when we distribute. Once we factored, we will set each of our factors equal to 0, so 4x equals 0 and x minus 3 equals 0, and solve for x. And when we do that, we find out that x equals 0, or x equals 3, and x equals 3. Now let's try this one. 3x squared minus 4x plus 5. Right, when looking at this one, it's not easily factorable. We can't solve by taking roots, and we're not told to complete the square. So we're going to use the quadratic formula. We need to identify our a, our b, and our c terms to plug into that quadratic formula. And we have negative b, we've got to plug in using parentheses there, negative b plus or minus the square root of b squared minus 4ac all over 2a. From there, it's just a matter of following the order of operations and computation. And when we do that, we get 2/3 plus or minus the square root of 11 over 3i. So clearly, that would not have been easy to figure out those roots from factoring. When using the quadratic formula, the value of the radicand, remember that the radicand is the number under the root symbol. So you have a root symbol, and whatever this term is, not always a number, but whatever this term is under the root symbol, that's your radicand. So it might be just a number. Some cases you might see a number and a variable. For us using the quadratic formula, we're only ever going to see a number. But the radicand is the quantity or the term under the root symbol. So the value of the radicand indicates the number and type of solutions. So before we even solve, we can look at that number that's there under the radicand, and it can tell us how many solutions we're going to have. That value this value is called the discriminant. And before we solve or start plugging into the quadratic formula, we can actually figure out the discriminant beforehand. B squared minus 4ac. In our quadratic formula, that should sound familiar to you, because it's negative b plus or minus the square root of b squared minus 4ac. So we can do just that little part of the quadratic formula, the discriminant part, to see how many solutions we should have. Let's see what this looks like. We're going to use the discriminant, which is discriminant equals b squared minus 4ac, and see how many solutions that we have. So when our discriminant is greater than 0 and a perfect square, that tells us that there are two rational solutions. So let's say we plug in some numbers and we get, in the discriminant, we get 25. 25 is greater than 0. 25 is a perfect square. So when we finish solving this particular problem, we should have two rational answers. Those are things that can be written as fractions. If d is greater than 0 but not a perfect square, maybe square root of 13, for example, we will have two irrational solutions. If d is equal to 0, we only have one rational solution. And if d is less than 0, like negative 8, for example, then we will have two complex conjugates. So we will have some complex numbers in there. Those are those numbers using the I symbol, those imaginary numbers. So let's put this in action and test some quadratic equations. Let's use a discriminant to determine the number and the type or the nature of the solutions. So here is our equation, 3x squared plus 5x plus 8. Before we put it into the quadratic formula, let's use the discriminant. Our a term, our b term, and our c terms have all been identified, and our discriminant is b squared minus 4ac. So we plug in those numbers, and we get 5 squared minus 4 times 3 times 8. Again, I would use parentheses here when substituting. When we simplify that using the order of operations, we get that d equals negative 71. If our discriminant is less than 0, going back to that previous chart that you hopefully wrote down in your notes, that tells us we will have two solutions, and they will be complex conjugates. Two solutions, complex conjugates. So something plus or minus, something I, and something minus plus or something I as well. Two complex conjugates. What about this one? Well, when we plug it into the discriminant, we follow the order of operations, what we get is the discriminant equals 0. Well, according to what we just wrote down in our notes, when the discriminant equals 0, we're going to have one rational solution. just one solution. So when we go through and we use the quadratic formula to solve this, if we get two different answers, we've